Please welcome Luke Parham.
All right. So yeah, this has got to go fast. That's Sonic the Hedgehog, in case you couldn't tell. And today we're going to talk about performance. And so just a quick introduction to me. I'm Luke Parham, as he said. I'm an iOS engineer at a company called Fusion. And I also do tutorials for RayWenderlake.com. I do videos sometimes and written ones sometimes also. And so I work at a company called Fusion, and we make these things called fuses, right? And it's kind of like a regular picture, but you can go ahead and grab it and move it around and see it move around in 3D space. And so if we take these, and if you're working on something like this, and you have a feed full of them, and your users can scroll around and tilt and, do all this stuff at once, naturally a lot of kind of performance bottlenecks end up cropping up in something like this. So this is kind of what I've been working on for the past couple years, working on the viewer for these fuses. So today we're just going to talk about a few of the things I've learned while I've been working on that. So why should you care? Well, I have a story about that. Way back in the day, there was this team working on something called the Macintosh, and it was going great. It was, much better than the Apple II in every way, pretty much, except for there was one big problem, and that was that the boot time of the Mac was actually just as slow as the boot time for the Apple II. And this is because there was bottlenecks around using the floppy disk to load data, and this made one Steve Jobs not super happy about it. So he came and he talked to the engineers, and he told them a little story to get them motivated. He said, let's say you can shave 10 seconds off the boot time. If you multiply that by 5 million users, that's 50 million seconds every single day. Over a year, that's probably dozens of lifetimes. So if you make it boot 10 seconds faster, you've saved a dozen lives. That's really worth it, don't you think? And I kind of like thinking about the story when I'm thinking about performance. It's kind of funny because by that logic, we could all delete Twitter, and then we would save millions of lives, but still fun to think about. So the game plan for today. First, we're going to talk about noticing dropped frames, what dropped frames are, and then we're going to talk about a few of the tools we can use to track down these performance problems. We're not going to talk about activity trace today, but there was a talk about this in WWDC earlier, so you can find that video and watch that. And at the end, we're going to have a bonus section where we talk about a few of the extra tips and tricks that I've learned. So first things first, dropped frames. So when you're thinking about performance on an iOS app, the first thing to think about is kind of what's happening and how rendering and stuff works. So we have this thing called the main run loop. And a run loop is just it's an object that manages a thread, right? This run loop manages the main thread, which is the main thread of execution of all the things in your app. So the main run loop receives events, like taps and stuff, and it delivers these events to the thread that it manages, the main thread. So basically, when your app's running, this is what the system looks like. It's always spinning in this loop and waiting for events to come in. And then when events come in, it it reacts to these events, and that includes drawing to the screen. So when you're thinking about performance, you have to keep in mind the fact that the system will try and draw to the screen 60 times every second. If you have a bunch of work that's happening on the main thread, let's say, then if this work is still happening when it comes time to draw that next thread, the system will actually just skip drawing that thread. It won't do anything, and it'll wait till your work is done. So that means you have 16.67 milliseconds per frame to get any of your work done. And this is, if it's a 120 hertz device, it's even less. And if you actually think about the time that you have to do work, this is actually only about 10 milliseconds because there's about 5 taken off the top, and that's due to system stuff that you can't really get around. So this is true for both the CPU and the GPU. Usually we don't do, a lot of times if you're working on a regular app, you don't really do GPU programming directly, but things you do can affect the GPU, and you do have to keep in mind that both the CPU and the GPU have to finish all their work in this 16 millisecond window. And this kind of brings us to kind of a topic to keep in mind when you're doing performance. There's actually 2 different things you should be thinking about. One is the raw speed of code, right? How fast does your code run? Do you have something that's just way too slow, slower than it should be? And then your perceived speed is kind of the responsiveness of your app. So when someone taps on a button or tries to push a view controller, does it stutter? Does it sit there and like make them wait and wonder what's happening? So a lot of times you don't actually have to make any code like technically faster, but if you rearrange things to be on different threads and not block the main thread, your app can look faster automatically to a user. So a lot of times responsiveness is more important. It's what gives your app that feel that users want to see. And then, so dropping frames, like I said, it can happen. This is kind of a thing about both, right? If you're dropping frames, you probably have code that's going too slow, and you're probably blocking the main thread and making your app unresponsive. So rule number 1 is to use a CA DisplayLink to track dropped frames. You can track frame rate in other ways using other tools, but actually seeing like when and where your app is dropping frames, an easy way to do that is to use a CA DisplayLink. So what is a CA DisplayLink? In case you're unfamiliar, it's a special type of timer, and it fires on the vsync. So the vsync is whenever your app has just finished drawing, right? So the nifty thing about it is that when this method, so actually, sorry, real quick. You set it up just like you would set up like a gesture recognizer or anything like that, right? You make a CA DisplayLink object, and then you give it a target and a selector. So every time the screen is trying to be drawn to, this method will be called, and you'll know that a draw has happened. Let's say that your app had a lot of work going on, and it took a while, and it dropped a bunch of frames, right? The link object that you receive, it'll have a timestamp on it. And if the timestamp that happened now is longer than 16 milliseconds since the last one, then you know a bunch of frames have been dropped since the last time this was called. So to see that, we can just have a method. Basically, all this is doing is kind of keeping track of when is the last time your app was drawn to, or when is the last time the screen was drawn to, and what time is it right now. And if you use math, you can see, okay, it's been X number of milliseconds since the last screen draw. If it's more than 16.7, we know that we've been dropping frames in the meantime. And you can get more sophisticated with this, right? You can track frame rate, you can log what's happening during this. But this is what we'll use to kind of see where our problems are when we jump in a time profiler. So here's a quick example of some bad performance on iOS. We have this app. It's kind of like another app, but better because it's all cats. And on the left side, you can see every time we have these big stutters sometimes when the cats are coming in, right? What you'll see over in the logs is exactly when these stutters are happening and how long they happen for. So once we know we have a problem, there's kind of a common workflow we'll use to kind of try and solve it. First, we decide there's a problem, and then we analyze with instruments, and then once you've analyzed a little bit, you can form a hypothesis. And then once you have a hypothesis, you want to go in and change your code, see if what you thought was causing the problem can be fixed. And then once you've changed the code, run your app again and see if it's actually been fixed. If it hasn't, then you still have a problem, and the loop just keeps going, right? And this is basically the scientific method. If you're trying to track something down, you want to be very systematic about it and not kind of just try things randomly, hoping that they'll fix the problem. So the big one we're focusing on is analyzing with instruments. And the first one we'll talk about is time profiler. Time profiler is kind of that 80 or 90% of the time tool you want to reach for if you're working on these kind of performance issues. There's a bunch of other tools, and they're all nice and can be very useful for different things, but I'd say 95% of the time, time profiler will give you a good look into what the problems are in your app and show you how to go and find and fix them. And so time profiler, it does focus on the CPU. Remember I mentioned that the CPU and the GPU have to both live within this 16 millisecond window. The time profiler instrument will tell you all of the code that's running on your CPU and how to make it fast, or where the problems are there. So here's an example. Here's an example of a trace in time profiler. And when you come in here the first time, it can be pretty intimidating, right? You'll see all these methods that you didn't really write and you don't really know what they're doing, and there's just a lot of information that can be kind of overwhelming. But if you dig into it long enough, it kind of gets more familiar over time. So here we have the call tree. This is all the methods that have been run in your app while this session was running. So let's talk about that real quick, because it's not super obvious what's going on in there. So here's an example run of an app. As always, we have main, right? That's the main first function that gets called. And so what Time Profiler does is it doesn't actually take the average time that all these methods are running. All it does is it inserts itself into your code, and then it just takes snapshots every 1 millisecond, basically. So when it takes that snapshot, it grabs the stack trace and kind of puts that into the call tree. So first, we have a snapshot at the 1 millisecond mark. And our call stack is main, and that's calling foo, and that's calling bar. So we take these methods that are being called in this call stack, and we save them off into the call tree. So each of them has been called one time, and it's in this order, right? Then, 1 millisecond later, we have main calling foo, calling bar again. So we capture that stack trace, and we save it off into the call tree. And this time, we just increment all these counts, right? They've all been called 2 times now. And then on the third call stack, we actually have a different stack, right? We have main, and it's just calling bar. So this time, so before we had main calling foo, right? And this time it's calling bar directly. So we actually have a branch in our code. Sometimes main calls foo, and then other times main calls bar. In this case, it's done the first thing 2 times and the second 1 time. So this is kind of how these different branching options happen in the call tree. Then on the third one, we have main calling foo, and that calls baz. And the interesting thing about this call stack is that this baz method has already been fired 2 other times, right? But it's so short that it wasn't captured in these traces just by chance. And this is actually more of a feature, right? Because if you have functions and stuff that are so short that they don't really, amount to much work in your app, they won't end up showing up in your traces because, they aren't that big a deal. So your call tree that you end up getting won't show you every single thing that's happening in your app, only things that are significant enough to, warrant showing up. So we have a new branch in our call tree now. So we bring that over. And then we have our completed call tree with all the different branching options. So that's what we're seeing here, right? We have main and the main thread, or we have the main thread and then all these methods that are being called as a result of that running. And then if you want to switch from the call tree, you can switch into the console mode. And over here we can see all of those dropped frames that we were talking about earlier. So now that you're in Time Profiler, you have a nice timeline pane up top. And you can kind of look at these dropped frames, kind of hone in on them, and say, okay, well, I have a bunch of things that are, a bunch of frames were being dropped at, 11 seconds into the run. So if we look up in the call, in the timeline, we can kind of see, oh, well, here's a bunch of CPU work that was happening during that. And if we click and drag on the timeline, we can actually zoom into just that section where all these frame drops were occurring. And then our call tree will be narrowed down to just what was happening during that part of the run. And then once you have it narrowed down, this is something that you kind of want to get familiar with. As I mentioned earlier, there's the main run loop, right? And the main run loop is what makes your app actually run. And so when you're drilling down into these call trees, this is the view you'll end up seeing like 90% of the time. You have main drilling down, and you have CF run loop run, CF run loop do observers, do source one, servicing the main dispatch queue, all of these things. And then each of these subtrees will end up containing like a lot of your big bottlenecks, or that ends up being the case. So, and then one other quick tip is when you see, how you have these disclosure triangles? Instead of just clicking through them one at a time, if you go ahead and hit Option click, and then click on one, it'll magically open that subtree to pretty much exactly what you're looking for. So if we Option click on this, it opens down here. And this is another thing that you might end up seeing a lot if you're in Time Profiler a lot. And if we look at this, this stack of all these methods and functions that are being called, we realize that there's nothing in this stack that we wrote ourselves. If you happen to be the person working on Catstagram, you would look at this and see, okay, well, I didn't write any of this code. We see this like CA transaction, CA render, all this internal Apple code, right? And so it's really easy to see this and kind of be like, well, I don't know what this is. I didn't do it. So I'm just going to ignore this. And there's an option at the bottom that lets you ignore Apple's code. But it's kind of hit or miss if you want to do that or not. Because if you see this, this clearly big chunk of code that is your biggest bottleneck, it's not always the best idea to just completely ignore it just because you didn't write it. So in this case, if we kind of focus in on this and do a little Googling and say, okay, well, what's actually going on here? We can see that we have this Apple JPEG decode image all. And we can see over on the left side that this function right here is accounting for 32% of the work on our main thread in our app. So if our app is stuttering, there's a really high chance that this 30% of the work is what's, causing the frames to drop, especially since we already narrowed it down to be in this region where all of our frames were dropping. So we know we have a bottleneck here. And how do we get around this? Rule number 2 is that if you're doing JPEG decoding, which you always are if you're loading images, a lot of times you want to end up doing it in the background. You don't always have to. If you have an app that has no frame drops and there's no problems, then don't worry about this. But if you have a feed and you have scrolling images, a lot of the times just setting an image on a UI image view means that your JPEGs will be decoded under the hood by the image view, and you can't really control it directly. But it is a bunch of work that is happening in your app. So the nifty thing is you can actually go ahead and get around this by just doing all the JPEG decoding yourself. So real quick, we'll look at this. This uses core graphics, and you just set up a context, and you draw into that context. So the resulting image that has been drawn here will actually be a fully decoded version of the JPEG that you had before. The kind of annoying thing is that when you're using UI images, there's actually no public API that'll tell you if a given UI image has already been decoded or if it hasn't been. So if you end up using this kind of a strategy, you kind of have to keep track in your own app, like, is this image a decoded one or not? Make sure to cache it properly and reuse them, because they are really big, they take a lot of memory, so you want to be sure to be careful when you're doing this kind of thing. But the nifty thing about doing this is that it is technically less efficient than letting the image view do things itself. But you can jump onto a background queue, do the decoding there, and this means that if you're on a phone with more than one core, which is all of them now, you'll automatically get multi-threading when you're doing all this JPEG decoding. Then when they're done, you can just jump back onto main and then set the image with this new decoded image. And then a quick aside, if you are doing something like this, you have to be conscious of memory warnings that happen in your app. So memory warnings happen on the main thread. And when they happen, you're expected to drop everything you're doing, clear any extra memory you have, and then react to them in time. If you're allocating a bunch of big images like this in the background, they don't actually see this, they don't see these notifications from the system that say, hey, I need you to clear your memory. So if you're doing something like this, the naive way, your background threads will keep allocating images while the main thread is trying to dump this memory. So if you're doing this allocation in the background, your app can get killed even though you think you're reacting to it. So just to be safe and make sure this doesn't happen, you can wait on the main thread from a background thread to make sure that you're not ignoring these memory warnings. So here's how you do it in both Objective-C and Swift. I kind of like the Objective-C version, but they're both good. And basically all you're doing is you're in the background, right? And you'll just send an empty method or just a nothing message to the main thread. And since the main thread is a serial queue, this message will ping the main thread, and then it'll wait for anything happening on the main thread to finish what it's doing. So if you have code on the main thread that's reacting to these memory warnings, when you ping it, this will cause your background threads to sit and wait while all of this reaction finishes happening. Then when it's done, this will return, and then you can go about allocating all your big images like you were planning to. So this is an example of after we've started doing the JPEG decoding in the background. And as you can see, there's not these big, sharp frame drops that we were seeing earlier. So there is trade-offs. Now you'll see that even though we had cats that had been loaded already, when you scroll back to them, you see a gray box for a second. So you kind of have to work around this by adding extra caching and making sure that you're managing your resources right. But overall, this ends up making the app more responsive. So. And so if we step back for a second, usually when you're thinking about, what are the things that are happening on the main thread to slow it down, you kind of tend to see the same things come up over and over again. So the biggest one by far is JPEG decoding in your average app, right? The average app is just text and photo images on a feed. And so the really big thing is JPEGs getting decoded. And like I said, UI views will do this for you lazily, like in their own time, but it does all happen on the main thread. Another thing that happens is text measurement, sizing, and drawing text all happens on the main thread. Hierarchy layout, and I think this becomes less true every year, but especially auto layout. Auto layout is pretty expensive, especially as you add more and more views that are all related. You can't really do it in the background. It all has to be in main. It's a very opaque system. And then even object allocation, especially in Objective-C, compared to simple operations like addition or things like that. Object allocation is like 100 times more expensive. So those are things you'll notice in your stack traces. And this is just a quick example. Once we've fixed the JPEG decoding, you don't see it in the trace anymore. But if you zoom in, you will see that the next biggest thing in the sample app is our NS attributed strings generating these NS attributed string objects. So it is a thing you can think about. You can, if this is still a problem, if your app is still dropping frames, you can always go deeper. There's always ways to get around whatever's happening on your main thread. But this is a very small problem in this example, but your app may be different. So, quick summary for the CPU section. If you can do work in the background, then you probably should, especially if it's a very big, long-running task, like decoding these JPEGs. Just make sure it's not any kind of UI kit stuff directly. We were using core graphics in that example, but even just allocating UI views in a background thread is not acceptable. You'll get weird crashes and stuff like that. But you can use core graphics. And then when you're doing this kind of stuff, ignore Apple's code at your own peril. So when you start using Time Profiler, you'll definitely have this tendency to want to just look at your code, hide Apple's libraries, look at your code and say, okay, what am I doing wrong? But that's not always the best option. And I mean, sometimes it is, but it's not always. And then don't forget about memory warnings, like I said. Okay. And then the next instrument is core animation. So where the Time Profiler would help you with things that are happening on your CPU, right? That's how you'd measure those. Sometimes you write code and it indirectly affects the GPU. And that's what the core animation instrument was always for. So basically, there's this thing called the render server. And it's an out-of-process system that does all the rendering for all the apps in the system. So all UI views, they implicitly cause a CA transaction to be created every time they are changed. So if you make a view and you set its bounds and you put it on the screen, what happens under the hood is a thing called a CA transaction is created, and it's shipped off to the render server. So like I said, it's an out-of-process service. It maintains a copy of your view hierarchy, and it takes care of issuing all the draw calls to the GPU. So sometimes, like I said, you'll write code that indirectly hurts the render server. And the core animation instrument has always been the way that you would track these things down. But apparently it was deprecated recently. So all of these little options here at the bottom, they are very useful, and they've been moved into Xcode. So you don't even have to fire up instruments anymore. Anytime you're running an app, you can just use these debug options directly from Xcode. So it's actually pretty nice. So if you go into debug, debugging, rendering, it's pretty far to get there. You can find we have these color blended layers, and let's zoom in on those. So we have all these options, and these all will hint at something you're doing wrong. It's not always super obvious exactly what it is, depending on the option, but they are pretty handy. So we'll focus on color blended layers first. And the nifty thing about this is when you start using these coloring options, it actually affects the entire system. So if you go out, you can see how your, the Springboard and any other apps are affected. So that brings us to our next section, performance police. We're going to look at some apps, and we're going to judge them very harshly. So first up is iMessage. That's right, even Apple makes mistakes. Nobody's safe. And here we see that all of these text labels are red, right? So the option we chose was color alpha blending red. And usually alpha blending is a totally fine thing to have if it's what you actually want. But in this case, we have white labels, and they are put on top of a white background. So the render server is calculating what the alpha is for white blended with white, which is white. And it's not a super useful calculation. So you're doing all of this for no reason, basically. So rule number 3 is avoid unnecessary alpha blending. And this isn't like a huge hit, right? This is kind of a, not a huge deal, but it is basically something you get for free, and you might as well not do it if you don't actually need it. So if you notice that you have this in your app, there's a really easy way to fix it. Just to make sure any of your views are opaque, and make sure they actually have a background color set. So those labels, all of your UI views probably default to a background color of clear color. So if you just throw a label up on a white background, it'll be clear, but if you don't want it to be clear, then you can just set it to be white, and it won't do any of this alpha blending anymore. The opacity thing, usually it defaults to 1, so you don't actually have to set that. But if you, maybe this is being set by somebody else, or this has changed. If that's the case, then you can change it back. And then next, we'll look at off-screen rendering. So one quick thing to note here is that whenever you hear people talk about off-screen rendering, it's kind of weird because there's kind of 2 different versions of off-screen rendering people are talking about. So sometimes people will say off-screen rendering, and they'll mean the core graphic stuff that we did earlier, right? We were taking images and we were rendering them with CPU code, and that's technically off-screen. We're not rendering it with the GPU, we're rendering it with the CPU. But that kind of off-screen rendering is one of those things where sometimes it's better, sometimes it's worse, and it's kind of a pros and cons thing. The off-screen rendering that you see in the core animation instrument and in these new debug options, this is talking about GPU-based off-screen rendering that happens on the render server. So if you see this, that means you did something in your code that when it got to the render server was trying to issue draw calls and render, and then it got to a part where it didn't quite know how to draw it, so it has to stall the GPU, jump back to the CPU, do some calculations, and then go back to drawing with the GPU. So doing these kinds of big stalls on the GPU can cause your app to slow down way more than alpha blending or something like that. So this is a pretty big deal. If you see a bunch of yellow in your app, that's something you kind of want to avoid and try to fix. So here we have Instagram. And if you notice these who to follow bubbles, depending on your phone, honestly, even on my 6S, if I scroll past these, I'll notice noticeable sludge as I go past these bubbles. And I would say the probable reason for that is they have a bunch of off-screen rendering that's happening here. So in this case, you don't want to use the corner radius property. This is one of a few properties that if you use it incorrectly, it'll end up causing your app to do off-screen rendering. There is a fix for this in I think it was in iOS 11.3, but it doesn't quite fully fix it. So now it's kind of a crapshoot. If you use the corner radius property, you might get off-screen rendering, and you might not. If you're lucky and you don't have it, then it'll actually show up green instead of yellow. So that's how you can know. But if you want to avoid this corner radius property altogether, you can just go back to our trusty core graphics stuff, and in this time we can use Bezier paths to define the circle. So here we have just a simple function where you pass in a regular image and you can get back a circular image. So this one uses the UI graphics drawing stuff, but if we kind of zoom in here, we see that we use a UI Bezier path. It takes in the rect and what we want the corner radius to be, and then we just draw with that instead. So we add a clip to our path, and then we draw. And this returns a version of our image that has a circular version of our image. And this way, the image will be a circle, and we won't have to mess with our views having round corners. So here's the last example. So this is in the Twitter profile app or section. And when it loads this text, this is a real-time view of this animation running. And then when you try and scroll up, it thinks about it. And eventually it goes. So this is on I think this is on an iPod 5G, but it's still super noticeable, even on a 6S or a 7. So go ahead and try it out for yourself. But yeah, so I wasn't even sure how they got so much off-screen rendering in that text. But one way that I was able to make it perform badly was to use this should rasterize property. So if you have a bunch of text and you're rendering it, you can use, for any view actually, sorry. If you have views that you're rendering, you can use the should rasterize property And there's a bunch of special rules around it. Like you're not supposed to use it on more views than will take up 2.5 screen worths of pixels. There's a bunch of weird rules, and basically if you break any of these rules by accident, then your app is guaranteed to off-screen render on every frame of your scrolling. So I don't think it's worth the risk usually. There's a lot of better ways to make your app faster. So I usually try to avoid this should rasterize property. It's really easy to fix this problem if you see it in your app. You just don't do it. It's great. But yeah, so that's this. When you're thinking about the core animation stuff, there's basically a lot of options in there, and you can go in and see if your app is doing anything indirectly to cause bad performance. The two of the big kind of obvious ones to fix are blending, so make your views opaque when possible, and then off-screen rendering is the much bigger one. So there's a bunch of kind of common things to do it, but try not to use the corner radius property, don't use should rasterize, and then shadows can also cause it. There's kind of a right way and a wrong way to do shadows. It depends on if you're doing text shadows or regular like UI view shadows. But with either one of them, you can either use Bezier paths for the UI view shadows, or you can use an NS shadow object with attributed strings to add text shadows. Don't just do the layer.shadow stuff if you can avoid it, which you can. And then UI visual effects views. These are really cool and can do neat stuff for you, but they are also super expensive. So if you're using a blur or anything like that, make sure to limit it to a very small, non-animating part of your app, unless you want it to be, pretty slow. And with that, we come to the bonus section. So just some quick, fun little things I found. So this is an example that I found while I was working on our camera. At Fusion, we have a bunch of AR effects in our camera, right? So you can make a fuse, you can find an object and go around them and make this fuse, but you can also add all these AR effects, and we have guides and stuff like that. So at some point, our AR effects were super slow, and so I jumped in and tried to do some profiling in Time Profiler, and what I saw was that if I zoomed in, we had our super secret AR effects, right? And these were accounting for 26.4% of the work on the main thread. So this is a big chunk of the work. But if you look right under it, boop, you'll see that the biggest thing that's happening in here is this NS dispatch data, get bytes in range. And we did have a part of our code that was right in here that was doing an NS, we were making an NS data for a chunk of memory, and then we were calling this get bytes to kind of transfer chunks of float pointer memory over to some other location for whatever reason. And so this ends up happening, it can end up happening where you get to a point like this and you see, okay, this is just a regular foundation object doing a very simple thing. How do I get around this? How do I want to move these bytes, right? So what do I do? And the answer a lot of times is to jump down into C or C++. A lot of times there's stuff that you could be doing with, a foundation object like NS data that you can also do in C, and maybe it's a little harder, takes a little more, work, but it ends up being a little bit faster. So in this case, C has a thing called memcopy, which I'm sure people have heard of. And so the bottleneck was, taking this NS data and moving memory. Instead, we can just use memcopy. And if you compare, the APIs for this, it's almost the exact same thing. We have data, we're getting bytes in a range, and we do this NS make range stuff. In C, you do almost the same thing. You pass in the pointer, and you do some pointer arithmetic, but it's the same math, and it's basically the same thing. So what happens when we swap out our NS data for a plain old C memcopy? The super secret AR effect that was taking 26.6% is now taking 0.6%, and now all this stuff with NS data is gone. So this one line, it's not even a full line, right? It's half a line of change. Ended up speeding our camera up by aggressive amounts. So that's just something to keep in mind. If you're ever kind of stuck at some ObjectiveC or Swift thing, think, okay, well maybe I can do this a C way and it'll be faster. I thought that was cool. Rule number 2 is avoid overdraw. This is something that can be true. Let's say you have a loading circle, right? The progress indicator that tells you how fast something is coming in to be downloaded, a lot of times that'll end up, being updated faster than 60 frames per second. So if you're trying to map something that's happening in your code to some, UI element on screen, you don't always want to update it like exactly as fast as it's happening. So to avoid this overdrawing, you can use the CA DisplayLink again, but this time you actually use it for kind of its intended purpose, for kind of drawing on screen, as something's happening. So you can use the preferred frames per second. This is something we've used in our fuses. So showing a fuse on an old phone, right? You can show that at 15 frames per second, and it'll look okay, looks about right, and it avoids, the twice as much work that would happen if it was running at 30 frames per second or 60 frames per second. So this is something you can kind of use to throttle drawing if a certain system needs drawing to be throttled. This is available on, the frames per second is available on iOS 10 or higher. If you're on an older one, you can do it manually, so it's not that big a deal. But basically just have a display link, and like I said before, you have a method that gets called every time the screen needs to update. And then rule number 3 is that you can use imp caching. So this is kind of more like an advanced thing. If you, let's say you have a function or like a loop, right? And all it's doing is calling some method. And you do some tracing and you find out that just calling this method is basically accounting for a ton of the work. And you'll figure this out by seeing that there's this Objective-C message send. When you look at your trace, you'll have a method call, and then you'll see Objective-C message send, and it'll say, taking this amount of the work. If this ends up being the case, which it can be if, like I said, if you have a really tight loop and you're just calling a method a bunch of times, what you can actually do is you can take advantage of the way Objective-C works, and instead of calling this method a bunch of times, you can actually reach into the system and grab the function pointer that this method ends up calling. And then you can save this off into a variable and just call this function directly instead. So the syntax for it is not super pretty, but this is what it looks like. You have a frame imp, which is the implementation, and you do all this little magic you call method for selector, and this will return the function pointer. Then later, once you've saved off the function pointer, you just call it like a regular function. And this ends up making this line of code around 2 times faster. But if this is a big deal, and like if you have a for loop that's running and you have 10 methods that you're calling in it, maybe they all need to be cached. Or maybe you can just write them all as C methods, or functions, I mean. But this can end up doubling the speed of a little chunk of code just by calling this directly. So kind of cool, kind of a nifty trick. I thought was interesting. And then bonus rule number 3 is that you can go even crazier and not use arc. So this is, once again, only an Objective-C thing. So this implies that you can not use Swift, which is very offensive to some people. But yeah, we haven't actually tried this in our app because it's an older way to do things, and not a lot of people are super comfortable with it. But if you do have just a system that can benefit from this, I've heard people talking about doing it, and I think they said like their code, that chunk of code that they took arc out of, ended up being like 100% faster, just because of all the like retains and releases that didn't happen as a result of doing it yourself. So kind of cool. But anyway, where to go from here? If you want to learn more about this stuff, if you think performance is cool and this time profiler stuff is interesting, then there's a book called iOS and macOS Performance Tuning. It's by Marcel Weyer. And I thought it was a really cool book, really a lot of interesting stuff like this. He is a real Swift hater. He's got a chapter on that, but, it's interesting. And then there's a bunch of videos online. Like I said, I do rate Winderlick, so I have a course on instruments. And it might be a little outdated now, but it's got all this stuff. Plus, it goes into like the memory debugging and battery stuff. So that's up there on Ray Winderlick. And then every year, DubDub has 3 or 4 videos about performance. So there's a lot of really good ones out there. And then as far as me, I've got a blog that I write on every couple weeks, I'd say, and then I also post to Twitter a lot, so feel free to follow me there. And now that you've learned this, go forth and make Steve happy.
We have a few minutes for questions.
I guess this is not the same topic, but this is probably in the WDC videos, but sometimes even if you throw things in a background thread, you just might have so much going on there, it slows down the main thread too, right? Yeah. So that's a CPU profiler, or?
Yeah, so
or what the name of it
if that is the case, you'll definitely see that. So when you are in time profiler, you separate, like things by default will be separated by thread.
Yeah.
But you can undo that kind of, and you'll just see all of your code. And so if your system is going super slow and you don't have anything on the main thread, it's easier to just put it all together and see what is your biggest bottleneck. Because that can happen where you have a bunch of stuff happening on these background threads and the whole system's slowing down.
Okay, and there's WDC videos on that, I'm sure, right?
Yeah, yeah, there's
tons.
Yeah.
Okay.
Yeah, exactly.
All right.
All right.
Let's thank our speaker again, and that concludes our second day of talks at AltConf, and we'll see you all tomorrow.
Cool.